My name's Jordan Appleson. I'm the CEO of Hark, and appreciate the intro, Dale. I know it's a bit of a mouthful to say kind of real-time market performance and analysis data processing systems. But that's kind of been my background for the last, like commercially, especially for the last several years, designing systems to stream and analyze real-time data. Since kind of starting Hark back in 2016, that has been still a core focus of what I do day to day, but really driving forward something that has real world change. So that's physical assets. Today, I'm going to be talking a bit about generalized anomaly detection for preventive maintenance and predictive analytics, and mainly the challenges of building this. So a little bit about Hark first. We're a software technology company specializing in kind of energy analytics and industrial IoT. So what we do is essentially connect to all these different industrial assets that might be used for manufacturing, renewables, even in supermarkets for refrigeration systems, asset control. And ultimately our intention and our mission is to help improve efficiency, maximize yield, and reduce waste. And that's improving efficiency of systems, maximizing the output. It could be of manufacturing processes, and reducing waste. And a lot of that is waste energy at the moment. Our technology itself is basically a platform that allows us to connect to any industry standard sensor, PLC, building management system, monitor sensor data in real time, store it, and then analyze it, and more recently, control. So the kinds of things we do at Hark are connecting to real-time, connected to energy systems in real time. So that's real-time power information, energy, consumption. We've got life sciences companies that are making drugs and monitoring oxygen, CO2 for them. We also do a little bit of pollution monitoring, or have done in the past. And really any kind of sensor that's available, whether it's on a production line or in a building or on a system, we should be able to connect to with that kind of plug and play fashion. And what we're focused on really use case wise is energy management, facilities and asset health management, so maintaining the health of an asset, in an industrial maintenance. So a little bit of context around like today's kind of talk and session. Essentially, what I'm going to talk about today is anomaly detection. But before I do that, I want to talk about some context around what we're going to talk about in terms of what we're connecting to and those assets, as well as why this is kind of an important thing. So in terms of industrial assets in the Hark world, or in the area we work in, that's typically, processes that are powered by assets. So that might be drives, motors that are driving, lines. It could be compressors, which are used for air or refrigeration systems, because typically they use compression to actually cool. And that, fridge plant alone has so many moving parts. Heavy machinery, so these have process automation controllers. All of these have process automation controllers, which typically have sensors connected to them. And that's where we connect into. We're not a business necessarily that go and put sensors in, because typically they already exist. And that could be furnaces, that have got, parts for planes in it that are curing different items, stability chambers for life sciences, like I've mentioned, and tons more. So all of these things have sensors in them. They're all part of industrial and manufacturing processes, whether it's for food or parts, or it could be even gases that are flowing through different systems. They're all powered by these assets. And ultimately what we're looking at today is how do we detect problems with them. So that's a little bit about like what, but why would we want to be doing something like this? Well, if you look at energy by industrial process and industry, this graph basically shows a little bit about the spread of different processes that are used in different industries for manufacturing. So if you're doing food processing, which is the first one on this graph, just a bit of background. On the left-hand side, on the y-axis, what this is millions of tons of energy, an equivalent. So it's kind of hard to kind of put all energy for all processes into kind of an equivalent basic relative index. So this is kind of million ton of oil equivalent. So in terms of food, as an example, what you'll find is that a lot of that is process heating. That makes up most of that industrial process. If you look at textiles and clothing, well, that's less about process heat and space heating actually takes up quite a bit of that. If you look at things like refining, like so for refinery of like oils and other things and metals, that's again process heat, drying and separation. There's other in there, which could be anything. There's compression, so compressed air, and all the way over to sort of other engineering industries where you've got low temperature processes, high temperature processes like basic metals, cement. All of this is powered by these industrial assets, right? And that goes into this process. And it's, if you look at it, you know, you've got refrigeration, you've got lighting, you've got compressed air, you've got motors, you've got separation, you've got different types of processes. And ultimately, these are controlled and powered by assets that we connect to. If we look at this by the actual cost, right? Like what this graph shows you is that actually the output of that process, what is the percentage of energy in terms of cost? So in the case of meat, the total amount of energy to produce a product for that individual item can be roughly about 2%. If you look at something like paper in the middle, you can see 10% of the manufacturing of paper is typically the cost of that is energy in the industrial process, and it goes on and on. And if you look at this graph here, we've got processing of meat, fish, oils and fats, dairy, flour, bakeries, animal feed, alcohol, soft drinks, tobacco. This manufacturing, manufacturing is so broad, right? And this actually plays into what I'm going to talk about a little bit more next. There's so much that goes into these processes, which may be powered by gas, it may be powered by electricity or other oil products. And obviously with the decarbonization of the national grid, coal is being phased out, and I'm sure everyone's seen this in the past. So on to a little bit about anomaly detection. So what is it? So given a sequence of values, produce a corresponding output sequence of values that denote whether each input that's coming to the system is anomaly. And that could be in real time or offline. And what we're trying to say here really is, I have some time series data. It's a line, it goes up and down. Which things look strange? Which things are anomalous? Which things do I need to know about? Bearing in mind that we've just talked about how many different types of processes there are, how many different types of system there are. How do you generalize that problem? How do you apply anomaly detection to all these different systems? Because they all have different patterns, and I'll come to that in a second. So why would we want to do this? Why is it important to maybe have a look at anomaly detection for this preventative maintenance and predictive analytics? Well, downtime of any asset costs money. It's expensive when it's planned. It's even more expensive when it's unplanned. So having some kind of system that can detect anomalies without humans having to look at graphs all day it will drive benefit, because if you know something's going to break or has broken instantly rather than an hour after the fact, that's an hour of time saved, or if it's preventative, an hour of time that the system wasn't down. And those costs can rack up, especially depending on the industry you're in. Asset performance alone impacts output. So the performance of an asset over time, it directly correlates to literally the output efficiency, the overall equipment effectiveness, and even sustainability. If you've got systems that are meant to be operating in a specific level to get the same output, but are operating with higher energy consumption, working harder for no reason other than maybe it's a faulty part or something's going to break, or it's a faulty gearbox in a motor or something like that, then that has a direct impact on your energy bills and ultimately sustainability. Reactive maintenance, like we kind of just mentioned, that can be too late. So for instance, knowing something is going to break a week beforehand, or has a chance of breaking, or maybe has some kind of problem a week beforehand, gives you time to rather than react to something breaking, gives you time to proactively analyze the situation and plan in the best course of action. And that basically reduces the requirement of reacting to something, but also it also reduces kind of downstream consequences as a result of product loss, right? i.e., I've lost some products in the life sciences industry, for instance. If you're storing drugs or compounds at a specific temperature for long periods of time, that's regulated. If it goes out of tolerance for more than a set period of time, you will have to potentially bin that product, and that's potentially millions of pounds worth of compound. We've seen this in the past with vaccines not being stored at the correct temperature, that have then been shipped out and then given to people, and they have basically been ineffective because they've not been stored at the right temperature, and no one's noticed. And last but not least, well, if you've got thousands and thousands of sensors across your estate, that's a lot of graphs, that's a lot of manual alerts to set up, and that's a lot of data to sift through for any human. Looking at thousands of graphs is not the best use of time. What we really want to be doing is looking at all the things that could possibly be going wrong with a high degree of certainty. So what are some of the challenges when you're designing like anomaly detection? So time series sensor data, temperature, humidity, light, CO2, power. What are some of those challenges that we face when designing something that essentially needs to basically tell you that something's gone wrong before it's gone wrong, right? Well, the first challenge, and this is one of the hardest things when you're designing any kind of machine learning model or statistical algorithm to deal with this, is domain generalization. And what this means is that we've just discussed that there's different types of processes, different types of sensors. Well, in different industrial scenarios, that typically means different patterns, right? So temperature for a fridge might be very different from the temperature outside, right? Because, a fridge might be going on and off, trying to keep a specific temperature, whereas a different asset might have a completely different pattern based on its usage. So if it's a heater, if it's a compressor, if it's, hey, how many numbers are coming out of my processing line, right? You have a you have to apply a generalized algorithm to that. It's potentially not going to work, right? Which means you go down the route of creating maybe a specific algorithm for a very specific industrial process. Well, if you design a very specific algorithm or a very, very specific model for that specific domain, well, that's great, and typically they will garner more accurate results. But what happens if the pattern changes? What happens if the asset itself, the way it's used, changes? Well, then it becomes useless potentially. The forecasts that you are doing for anomalies or the classifications of anomalies, they become less accurate over time, which means you've got more upkeep on a very specific model or algorithm. And that also means that you can't just apply that to, oh, I've got a fridge over here, but I've got a melter over here. You can't actually apply that same model, that same algorithm to everything. And that's a problem in itself, right? Because you can invest a lot of time designing a model to do one specific thing, but you might have 100 other types of assets across your estate, and you might have to do that for the same, basically, for all of those assets every time. So that kind of covers kind of the fact that different algorithms may be required for different patterns. But the other thing with that is that different algorithms and how you configure them typically work well on certain types of data and not on others. For instance, Holt Winters works really well on seasonal data, whereas with stationary data it can show quite poor results, right? And that also feeds back into the outcome of, well, I just want to be able to apply anomaly detection to any of my assets and get a reasonable accuracy around whether or not there's a fault, or there will be a fault. So what does this look like actually in practice? Well, this is an example of stationary data. So this is something out of our platform. This is humidity, and you can see this is stationary. It's very stable. This is a domain of stationary data, right? Typically a flat line, right? So as human beings, and I'm going to talk about this a little bit more, as human beings, we look at that and we go, well, it looks like a flat line. Okay, so if there was a massive spike in this data, you'd probably look at it and go, oh, that looks like an anomaly, right? We see a line, and we can, as human beings, our brains can, using something called visual saliency, like we can see that there isn't really any problems with it. I can't really see any anomalies. I mean, whether or not some of these spikes, these tiny spikes, are anomalies or not, it actually doesn't really matter, because it's not really this asset really needs to be at 60% humidity at all times, and it is. This is an example of seasonal data. So this is temperature, this is the fridge, and you can see that it has that seasonal pattern. It goes on and off in terms of up and down between kind of a set point of around 5 degrees, and it's always going up and down, and then what looks like maybe a 12, 8 hours, 13 hours, a seasonal kind of 13 hours, something happens, right? Maybe the door opens. I don't know if anyone's actually opening the fridge door at kind of 2 o'clock in the morning, but who knows? Now, is that an anomaly? The first time you see it, maybe it is, but actually if that continues to happen, you don't want to be alerted every time that you see this spike. It's a seasonal trend. It's a seasonal pattern. So we need to be able to make sure that if we're dealing with seasonal data, that we also can take into consideration changes in the seasonal patterns, right? Which in itself, how do you know it's an anomaly, right? How do you know it's something that's going to occur again? And then you've got non-stationary, kind of relatively unstable data. This is power. So this is kilowatts, instantaneous kilowatt values of I think this is an industrial asset, and it turns off and on quite a bit at fast frequency. How do you determine whether there's an anomaly with this data? If you throw something like Holt-Winters at this, or other statistical algorithms, everything on here that's above kind of 20 degrees, 20 kilowatts is probably going to be flagged as an anomaly when it's not. So going back to this problem of domain generalization, how do you design an algorithm? This is a challenge, right? How do you design something, not an algorithm, but a system, a whole system, because it usually is multiple algorithms, multiple models, to cope with all these different types of data. So problem number 2 is labels and features. So when you've got different types of time series data, what I've just shown you here on these graphs is minute by minute intervals of all these sensors. The sample rate is 60 seconds. That means for every sensor, you've got 1,440 readings per day. That means for 100,000 sensors, you've got hundreds of millions of readings per day. And we have hundreds of thousands of sensors in our platform. So it's simply impossible, if you're using a supervised approach, to manually label every data point as to whether or not it's an anomaly. Because 1, you don't know, and 2, there's millions and millions and millions of rows. I don't want to be the person going through all those rows and going, well, these are the ones that look like anomalies, and these are the ones that don't, and then do that again and again and again for hundreds of thousands of sensors. And what happens when you add more to the platform, right? You've got to do the same thing again. If it's a different pattern, if it's a different domain, you're going to have different labels for different sets. And that's a problem, because you want this to be efficient and time, within a certain time frame, you want to be able to get an alert, but you also don't want to have to spend ages and ages and ages tweaking the system continuously. And then more importantly as well, what happens when you've trained your model and it takes into consideration things like seasonality and what anomalies are in the context of that domain? What happens when you've not seen a pattern before? What happens when a global pandemic happens and everything just goes up in arms, right? Then all your models are broken. Like that's something that we've seen recently when we've been looking into some of our forecasting technology, that when you're taking into consideration, well, weekends and time of day and bank holidays, which all get fed into different models, that's completely gone out the window now because of COVID. And I'll give you an example of this, right? First things first, just to clarify, this challenge is I don't want to be the person labeling all of these manually, because I'll be here until Christmas in 1,000 years. And remember, data is coming in every day, right? So you've got the data that you're labeling and patterns changing, but you don't want to have to keep necessarily relabeling all those all the time. So this is example of what an effect of COVID on something that is a seasonal pattern. Yeah, this is an example. So with COVID-19, in 17th of February to the 20th of February, so 4 days, is a building load of a building at 60-second intervals. This is what a seasonal pattern looks like. Load every day, building is used, then not used. This is a month later. Same, Monday, the 23rd of March to Thursday, the 27th of March, the building is no longer being used. The assets in there are no longer being used in the same way. People are not going in. So that's totally broken models that take into consideration kind of weekly seasonality. So now you have to go back and forth and figure out how you're going to redesign, retrain it, but you don't have enough data. No one's seen anything like this before. So how do you label that? How do you train a model to do this? So last challenge, the business case. How quickly do you need an answer to the question? For preventative action, it might be minutes, perhaps hours. For predictive analysis, scheduling maintenance, I want to know all the anomalies that have happened. Maybe hours and days. So I'm conscious of time, because I'm conscious of time. So I'm going to whiz through this, and I have to take any questions. The business case has to focus around accuracy, time, and parameters. Supervised learning models they are typically, they have the best accuracy, right? But require a lot of labels and a lot of upkeep. And if you're dealing with large amounts of data that are subject to pattern changes, it's going to be a never-ending cycle of retraining and potentially not actually garnering the best business outcome. Unsupervised models, they require less labeling but result in worse accuracy. From a time perspective, if you've got lots of sample rates and you're trying to classify anomalies in real time, then you've got time constraints. You've got to make sure you can do a classification in kind of fixed time. And more accurate models usually require more time to process the classifications, which is a challenge. And then you've got parameters. When you're dealing with generalized anomaly detection, you don't want to have to tweak lots and lots of parameters. Tuning high parameters on a business case by business case basis is not an ideal place to be. So last but not least, I'm going to talk about how kind of batch anomaly detection versus online anomaly detection. So batch anomaly detection, i.e. take all the data, run something on a batch, maybe at the end of the day, and then output all the anomalies. Pros, there aren't really any time constraints to this as long as it's processed within a fixed amount of time, maybe overnight. It's easy to spin up infrastructure in the cloud and pay for what you use to go, all right, spin it up, calculate some anomalies based on what I've seen in the past day. And it allows us to use kind of the entire data set. Slower models, slower algorithms are acceptable here. But the cons of this are that because it runs in batches, you might only be able to get your anomalies and your output for preventative maintenance at the end of every day. That might be okay, but if you're trying to prevent downtime very quickly, then maybe it's not okay. And then the pros of online anomaly detection, conversely, i.e. as data is coming in, it's being classified as an anomaly, right, or not, is that it can report whether a metric is anomalous straight away. You might not want to alert someone to that straight away, and I'll come to that in a second, but the cons of that are that your system has to be very fast at those classifications. And from a time constraint point of view, you can't really use algorithms that take time to process because if you're getting data every minute and it takes 5 minutes to process whether it's classification, it might be all right, but if it takes 15 minutes and you've got thousands of sensor points, it's a problem. And the last thing around this is it needs a set of heuristics to calculate whether or not multiple anomalies are an excursion, i.e. I've seen 10 things happen in the last hour consecutively. I am going to send an alert versus I'm seeing an anomaly and it's a false positive, and then waking up everyone who's on call, which you don't really want to be doing. So just some final thoughts on this, and appreciate I've gone through this very quickly. This is one method that we've looked at to kind of get the best of both worlds, where we take sensor data in real time, and after a specific amount of time, whether it's several days, we can enable anomaly detection, recompute a forecast for the next hour, for the next n amount of time. It doesn't have to be an hour, and that forecast is then stored. The real-time process comes in, checks against the actual value against the forward forecasted value, and then checks it against a dynamic threshold, and then send an alert. This is a very I would say straightforward and easy to use kind of architecture that might not be that accurate because it depends on how you're computing the forecast. And I'm going to show you some final screenshots before I leave of why this might be a problem. But this is something that starting off, you get batch and some real time at the same, by processing a batch set of forecasts and then comparing real time data to those forecasted values, you can actually get the best of both worlds. However, the accuracy might not be great. So some forecasting bloopers before I go. Attempt number 1, forecasting some data. So the blue line is the actual and the orange line is a forecast. As you can see, it literally, I'm going to use the pun, fell flat on its face because it's almost a flat line. Forecasting bloopers take 2. Getting there, not really tweaking all these different algorithms. It might be part of this was to do with certain, I think, statistical, basically trying to do linear regression on this in a way that was just without the right amount of features. And then take 3 is actually this is better, but it's completely overfitted to it to be the point where it's almost too good to be true. So if you can compute these forward forecasts ahead of time and then compare these to the values within a dynamic range, dynamic threshold, you've got a way of almost getting to kind of real-time anomaly detection. The only thing that the problem we have with that architecture is that we need to be able to update weights and we need to be able to update the models as things change, which is a problem that we talked about in terms of domain generalization. So last but not least, a couple of methodologies, some things that we've been looking at in our quest for real-time insight. Start with batch analysis first. So batch analysis for forecasting, take that data, use it in kind of online systems if you can. It gives you the ability to look at accuracy and run different experiments in a kind of isolation of your production environment. Combining conventional statistics with machine learning, which is kind of what we've, you don't have to train neural networks to make forecasts like we were doing. You could just use, you just use any kind of forecasting system and then combine that with maybe some kind of dynamic threshold kind of component. That typically works. And then aggregating anomalies and then alerting. Don't alert on every anomaly. So that's something that we absolutely have to do, especially when you're dealing with real-time detection. So that's me. Thank you so much for having me, and I'm happy to take any questions.